This chapter discusses correlation and regression, which analyzes the relationship between two variables, and we refer to those variables as x and y. Section 4.1 focuses on scatter diagrams and linear correlation. When studying correlation or regression between two variables, we usually plot the data pairs of x and y on a scatter diagram so you can visually see if there is a linear relationship between those values. So the x variable is going to be called the explanatory variable, and the y is going to be called the response variable. I will use the guided exercise on page 134 as an example before we work on problems 10 and 12. So let's go there. Table 4.1 is a safety report that describes 7 divisions of an industrial plant's quarterly safety report. The X values right here represent the number of work hours used for safety training. And this is the explanatory variable. And the Y values over here represent the lost hours in each division because of industry-related accidents. So Division 1, they only spent 10 hours on safety training, and there were 80 lost hours because of industry-related accidents. In a scatter diagram right here, we plot the corresponding X and Y values, the paired data for each division. At this point, we can draw a best fit line, kind of in between these paired data, somewhere in the center of this scatter diagram, which we can also call a scatter plot. And I'm going to go to page 136 to show you that the line fits the data points reasonably well. So hang on. As you can see, the line fits the data points reasonably well. There are 4 types of scatter diagrams with a moderate to high linear correlation. So let's look at those. They are on page 135. A positive linear correlation is right here. As X increases, so does Y, and going from left to right, you can see the best fit line goes up. A negative linear correlation, where low values of X are associated with high values of Y, and going from left to right, the best fit line goes downward. If all the data points lie on the line, such as these 2 scatter diagrams, then that is defined as a perfect linear correlation, whether it is positive or negative. And in statistics, this almost never happens. Okay, in this particular scatter diagram with the safety report, this tells us there is a negative linear correlation, that the more number of hours spent in safety training, like here, 80 hours, then there is a decrease in the number of hours lost due to a decrease in on-the-job accidents. For example, look at Division 7. They spent 80 hours of safety training in the quarter, and they only had 12 lost hours of work due to industry-related accident. Let's talk about lurking variables. These are neither the X or the Y variables, which means they are not the explanatory or the response variable, but they may be responsible for the changes seen in both X and Y when you plot them on a scatter diagram. So example 3 on page 143, 144, which is right here, explains it quite well. Over a period of years, the population of a certain town increased. It was observed that during this period, the correlation between X, which is the number of people attending church, and Y, which is the number of people in the city jail, was R equals 0.90. Does going to church cause people to go to jail? Is there a lurking variable that might cause both variables X and Y to increase? Simply explain, the sample correlation coefficient R, this R right here, assesses the strength of the linear relationship between the X and Y variable. The closer the R value is to 1 or -1, then there is a strong linear correlation. In this example, where r equals 0.90, it is very close to 1.0, which means there is a strong positive linear correlation between the two variables. However, this data implies that going to church causes people to go to jail. This is where you have to ask yourself if there is a lurking variable or something else causing this correlation to occur. But the high correlation is probably due to a population increase in the town, which is probably the lurking variable. Let's go on to problem number 10 on page 145. Over the past 30 years in the United States, there has been a strong negative correlation between the number of infant deaths at birth and the number of people over age 65. A. Is the fact that people are living longer causing a decrease in infant mortalities at birth? And B, what lurking variables might be causing the change in one or both of the variables? And explain. Well, the first question asks us, due to the fact that people are living longer, is this causing a decrease in infant mortalities at birth? Well, looking at the question and the variables, they really don't have anything to do with each other. My answer would be no. And I would explain that while a correlation coefficient is a mathematical tool used to measure the strength between two variables, it doesn't imply a cause or effect between the two variables being tested. In other words, just because the variables may increase or decrease together, it doesn't necessarily mean one is causing a change in the other to occur. In this case, a lurking variable must be involved. And then, of course, B asks what lurking variables or variable may be causing this strong correlation. So a good example to lurking variables for this problem would be things like better health care or even better medical treatments. Let's go to problem number 12 on page 145. Problem number 12 says, do people who spend more time on social networking sites spend more time using Twitter? Special networking sites can be Facebook, which I'm sure most of you are aware of. Megan conducted a study and found that the correlation between the time spent on the two activities was 0.8. What does this result say about the relationship between time spent on the two activities? If someone spends more time than average on a social networking site, can you automatically conclude that he or she spends more time than average using Twitter? And then explain. This problem is asking us to interpret Megan's findings from calculating a sample correlation coefficient R based on the amount of time spent on social networking sites. After calculating this, she came up with an R value of 0.8. So let's talk about the sample correlation coefficient R. As I said earlier, it is a measurement of the strength of a linear relationship between two variables, x and y. At the bottom of page 136 of your book, you will find the definition. First of all, just as an FYI, the sample correlation coefficient R is also known as the Pearson product moment correlation coefficient, named after the statistician Carl Pearson, who has been credited for creating the formula. Okay, looking at the definitions here, if R equals 1, then there is a perfect positive linear correlation. If it is a negative 1, then there is a perfect negative linear correlation. If R equals 0, then there is no linear correlation. And of course, when we say R equals 1, R equals negative 1, etc., you know that there is a formula. So let me show you that formula real quick. This is the formula, this whole thing right here. Now, the formula itself may look overwhelming, but when I show you how to organize the data into columns, the calculation will not be difficult. For now, let's look at what your result will mean once you have calculated it. The closer to 1 or negative 1 your R value is, then the better the line will look if you created a scatter diagram, that best fit line, and it would be a strong correlation, positive or negative, respectively. And it would be a strong correlation, positive or negative. Let's go back to Megan's correlation coefficient R, which equals 0.8 right here. That would be a moderate correlation, and it is positive, which suggests that people who spend more time on social networking sites tend to also spend more time on Twitter. Also, you have to remember that these correlations are not 100% certain, so they're not set in stone. The next video will show you how to calculate problems 13 and 15 of this section. This is where we're going to go into learning how to solve that big formula.